Welcome everybody to another Spidey Physics video. Today we are going to do a general, simple introduction of vectors. Basically, I'm going to spew out all the knowledge I know about vectors and how I think about them. And I will do a secondary video on vector algebra, how to add them, how to subtract them, and how to multiply them together. So a vector is a mathematical object that is normally brought in and introduced alongside this thing called the scalar. So I'm going to write a scalar over here and vector over here. And I'm going to do just a little list of their differences. So a scalar is just a number, while a vector is a number with a direction. You can think about this number as magnitude. Maybe I'll do this. Magnitude. So magnitude, normally I hear this word magnitude with earthquake, 3.1 magnitude earthquake. It is just a number, and in physics, normally we describe things with scalars such as temperature. Temperature is just a number. 13 degrees Celsius, Fahrenheit, Kelvin, just a number. It has no direction. You could think also of mass, so 13 kilograms, pounds, whatever. No direction associated with mass. Same thing with volume. 3.1 liters, milliliters. Volume could be meters cubed. Whatever it is, also just a number. And I guess also a distance. Distance is a good one. So the store is 3 kilometers away from my home, or 4 miles, or you can measure distances of smaller things like centimeters, nanometers, micrometers, anything like that. All of these things are considered scalars. Meanwhile, a vector has a magnitude. So this thing is a magnitude, and it also has a direction. And it all normally has a picture associated with it. So people think of vectors as a straight line with a arrow. So this line has a specific length over here. It is the magnitude, the number. Maybe I'll do magnitude right here. And this direction, normally you need to have a direction with respect to something. So people like using the standard Cartesian plane here. If we have an x and y axis, and our vector starts at the origin, so the origin is right where the x and y axes intersect, then you can draw this angle here from the positive x-axis to where the vector ends, and this angle is the direction. A couple examples of a vector could be velocity. So this is normally in meters per second. Velocity is the vector version of the parameter we're talking about, and speed is normally the scalar version. So over here I can write speed. Your car normally doesn't tell you the direction you're going, right? Because you could just look out the front windshield and you'll see you're going forward. But it tells you the speed on the speedometer. So that is the scalar version of the vector. Another kind of thing could be acceleration. Maybe we could talk about force. That is another good one. So we have this object here. The force that it is applying down on the table is this force due to gravity, which is a vector quantity. It points downwards. Weight is another one. So weight and mass are kind of interconnected a little bit. And velocity and speed are also interconnected. The difference is mass doesn't change depending on the planet you're in. It's a property of the object. But weight is the mass of the object times the gravitational acceleration of the location you're in. So you have mg in this case. So yeah, these things have a direction. Weight actually is the force of gravity acting on an object. So these things are also a little bit interconnected. So yeah, I'm adding a bunch of physics knowledge in here, but really we're talking about vectors. So All of this stuff here is just to kind of make a distinction between scalars and vectors. So let's move on to another way of looking at vectors. Like I said, a vector is normally a property with a magnitude. Sorry, it's not a property, it's an object with the property of magnitude. This is the length of this vector. And over here, if we draw some axis, we can also say the direction. So this is what a vector is, something with length and direction. Interestingly enough, in math, there's a couple ways of describing this magnitude and direction. And one way is you can break it apart into components on a Cartesian plane. So let's say we have a Cartesian coordinate system right here, two-dimensional. This is x and this is y. You can also have a three-dimensional one right here with a z-axis, right? But we will not talk about that just yet. We're going to move on to three dimensions in a second. So I'm going to write two dimensions here. You can actually think about vectors as being multi-dimensional scalars. So this thing is 0 dimensions, and this thing is more than 1 dimension, right? Because well, actually, we will get to that in a second as well. Maybe I'll bring in like a number line, something like that. So, okay, let's say we have this vector right here. It is chilling in a, let's put it somewhere different. Let's put it right here in the negative location. So since I wrote that side as the plus x-axis, this is the minus x-axis. This is the minus y-axis. So as you can see here, we have a vector with a length, right? This is the length, and it has a specific direction. It's pointing this direction as opposed to this one, or this one, or anywhere else. And before I told you, you can take the angle going from the positive x-axis to where the vector is, and this angle is the direction. Normally, we like starting here as mathematicians, like everybody agrees that you start at the x-axis. It's kind of like agreeing that over here on a clock, midnight starts at 12 and the day also ends at 12. So we like to measure angles from this axis here. So technically, if you all agree on measuring a degree from there, you can take this degree here all the way wrapping around the middle of the coordinate system here and going to the vector, and this would be your direction. If you don't agree on that, you can just as easily take this angle here, or maybe this angle here, or if you want, you could take this angle here. It really doesn't matter. It's just convention that we choose an angle to start from the positive x-axis and wrap around until you get to the thing that you're measuring, in this case, a vector. So let's stick with that, right? What I was talking about with components is you can break apart this vector into its x and y components. On this coordinate system, we have the x-axis right here, and we have the y-axis, and all of these things are numbers, right, on the x-axis. I'm going to get to how we could use a number line a bit later, but I feel like most people are comfortable with this little Cartesian system here. So as you can see, the vector goes over here into the x direction. It goes slightly into the negative x direction, and it goes over here into the negative y direction. So you can break apart this vector by drawing these lines all the way down, these projection lines, until you get to over here on the x-axis. And then you can draw this component of the vector in this light blue line, which I will say is the x component of the vector. Let's say the vector is capital V, right? I'm going to draw this little capital V just to, in the same color as the vector, just to say that we've named it, right? So that is the Vx component over here. You could do the same thing on this side, make a little projection all the way to the y-axis, and this will use a different color for it, this dark green one. This is the Vy component. Now I'm writing Vy and not V minus y and Vx instead of V minus x because It's just a bit cleaner to look at something like this instead of something with these little minus signs. And eventually you're going to do equals and then write what these things equal to over here. And in those boxes, you can put those minus signs. So I'm just kind of showing you guys how you can break apart this vector into its own components. So once you break down a vector into these components, there's two ways of writing this vector. So we have here vector v. Actually, let me stick with the color scheme that we got going on here. I can say v is equal to, and normally you have vector with this little vector arrow on top of it, right? As opposed to just a thing like this, which does not have a vector line on top of it. Another way that textbooks distinguish vectors is they normally use a bold symbol to denote a vector. So you might see a bold symbol like this, or you might see a symbol that's not bolded with a little line on top, or you might see both like this. So I have here an equal sign, and what a vector is the length of the vector. So here I'm going to just draw these two lines which represent magnitude of v. So that's literally just the length of the vector, the length right over here. I'll do length. So you can literally measure this with a ruler, plug this number in here, and that is one component of your vector. Sometimes when people want to talk about the direction, they use this at symbol because they say a vector of length a or of length v or of length 12, whatever, at a direction of theta. And here theta could be like 190 degrees or something like that, or you can use radians, whatever it is. It's fine, you can use it. So here we have these two components of a vector, which is its length and its direction. And actually I will write in red here, direction. Now, why I'm writing this to you guys is to show you that this way of talking about a vector is the same as, I'm going to do an equal sign here, the use of the components. So here I can write the x components, and then I can do a plus sign. Actually, I will also write this at symbol in black just to distinguish between things a bit cleaner. So we have the vx component, and in green we have the vy component. Cool. Let me actually do this a little bit here. Boom. And I'm going to move this little direction thing right here. Boom. Awesome. So what we have here is another way of writing a vector. Here we have the x component of v. And over here we have the y component of v. So this is two different ways of looking at a vector. Two different mathematical ways. I guess the third way would be looking at it using this picture right here with the length and the direction. You could literally think of a vector as like a pencil pointing in a specific direction, or your finger, or any kind of directional object. Over here, I've written kind of the mathematical version of looking at it. You literally write the length of the vector at a given direction, or you can write the components like this. And normally in physics classes, this is the more used way because, you use a Cartesian coordinate system to set up problems quite a lot. And these things here are technically two vectors that if you combine together will give you the final vector. So over here, I have expanded the picture of the vector v and its components. All right, this is the vy component. This is the vector itself. And this is the vx component. So take a look at this. Let's say I grab this vy component and I duplicate it, and then I slide it from here all the way to here. You can see I get a nice right angle triangle right here, right? I can do the exact same thing with the vx component, duplicate that, slide it all the way down here, and I will just move this right here and move that right here. So if you take the components of the vector, you can slide them across and create a triangle like this, which is a right angle triangle. Or you could do it the other way around like this. That is literally taken from this picture here. So you can create this right angle triangle here, or you can create this right angle triangle here. You can always do this in 2 dimensions, 3 dimensions if you're working with a Cartesian coordinate system. You can do it with any further dimensions as well, but it gets a little more complicated once we get there. And the reason I want to show you guys this is because now, if you have a right angle triangle here and here, then you can use Pythagoras Pythagorean theorem, right? Everybody remembers this: a squared plus b squared equals c squared. In this case, a and b squared are the components. Vx squared plus vy squared equals v squared. So if you want to find the magnitude of the vector, which normally is written like this, then it is literally square root of its components squared. And that is literally taking Pythagorean's theorem and using that there. Cool. So if you are given the components, the things over here, then you can use Pythagorean theorem in every scenario, unless the vectors are not creating a right angle triangle, and you can find the magnitude of the vector. If you're given the magnitude of the vector, this thing here, it is a little bit more difficult to find these guys. You cannot do it unless you also have the direction. So let's see if we have these components here, how we can find the direction as well. Because if we can use these guys and find the magnitude and direction, then we should also be able to use the magnitude and the direction to find the components. Okay, so let's take a look at the direction. It's over here, again, from the positive x-axis all the way to the vector in question. And how I like doing this is breaking it down into 2 steps. The reason is, here, I technically am forgetting that there is a coordinate system over here and that this is the positive x-axis and that this is the angle that we're measuring. All I'm looking at is 2 right angle triangles, and I kind of want to find this angle theta here. But this angle is not the same as this angle. It is actually just this tiny portion of this grander angle here. So I like breaking it up into 2 steps. From here all the way to here is 180 degrees. It's a flat surface, right? 180. If you go all the way around, this would be 360. 360 divided by 2 gives you 180 here. So this angle theta is equal to 180 degrees plus this little question mark, which is the question mark over here, this tiny component of the angle, right? So once we look at this over here, we want to find this angle here. Let me label this angle as question mark, right? We're not going to use theta. You could use another symbol. I'm just going to use question mark there. The way you find this is, well, let's say we are given the components, either Vx, Vy over here or over here, and we don't know what this is. I just told you guys that if you have the components, you can find what the magnitude of this vector is, which is technically the magnitude over here is the length of this side of the triangle, the length of this, and it is literally found using Pythagorean's theorem. So if you have these x and y components, then you can find the length of your hypotenuse of the triangle using Pythagorean's theorem, and you can find all sides of the triangle. Now to find the angle, you can remember that we have this mnemonic for sine, cosine, and tangent. So sine O over H, so. Then here we have ka, which is cosine A over H, adjacent over hypotenuse. And then here we have toa, SOHCAHTOA. So this means sine, this means cosine, and this means tangent. These are trigonometric functions. I will maybe do another video on these later, but you could just take a look at your calculator and see what these guys are. And these things over here are opposite. That is the same as this. Then here we have adjacent, which is over here and over here. And here in orange, I will do hypotenuse, which is this H right here and this H right here. Okay, so what you need to do is once you have a triangle like this, you must label which side is the opposite, which side is the hypotenuse, and which side is the tangent. So I'm going to paste this right here, expand it a little bit, and I will write this in red. So if you take a look at this triangular setup, right, the hypotenuse is always the longest side of the triangle here. It's always this guy. So I will label this V as the hypotenuse, right? Now you have to take a look at what the angle is, where the angle is located. This is the angle we're looking at. And by symmetry, this is also the same angle right here. This angle and this angle are equal. So what this adjacent and opposite means is the adjacent side of the triangle with respect to the angle and the opposite side of the triangle with respect to the angle. So here we have the angle. The opposite side of this angle is the opposite side of the triangle. So this thing right here is opposite, right? I'm now going to write op over here. And same thing, adjacent side is the side that is directly adjacent to the angle, not this side, even though this side is technically also adjacent to the angle. Adjacent means next to, right? This long side is never the adjacent side. It is always the longest side of the triangle, which is called the hypotenuse. So the next thing here is this Vx, which we are calling the adjacent, like that. And similarly, if you had this side of the triangle, then the opposite side would be this, op, right? Which is the same thing as this side, the Vy. And the adjacent side of this would be this, adjacent. But it is not really too useful having multiple triangles like this and multiple angles. So normally I kind of just like looking at one triangle. So pick either this triangle or pick this triangle and then find the angle that you're looking for. The reason I chose this triangle and I wrote the angle over here is because the original picture we were looking at, the angle that we're looking for is the one right over here, right? Because if we add that angle to 180, we will be able to find this angle here. So I chose to use this triangle here because if I use this triangle, then I would have to find this angle here and then add that angle to this 180 to find the actual direction. So I just like using the triangle that is right here, if that makes sense. So now that we have this set up, we can take a look at this sine, cosine, and tangent. And the way I like setting up these things is here, I will do it as 1, 2, 3 for sine, cosine, and tangent. I look at SOHCAHTOA and I write down the first letter that I see. So here I see sine. Sine normally eats like a thing here. The thing it eats is an angle. So I'm going to write sine. For the second one, I will write cosine because I see the C. And for the last one, I will write tangent. These are, again, functions in your calculator. Then I'm going to leave this thing blank over here, and I'm going to do an equal sign on this side of the equation. What we want to do is use this SOHCAHTOA mnemonic to create an equation. And the equation we're going to create after that is literally what you see over here. Opposite over hypotenuse, adjacent over hypotenuse, or opposite over adjacent. Does that make sense? So for sine, we have opposite over hypotenuse, which we have as opposite is Vy. And the hypotenuse is just the V, the magnitude of the entire thing. For cosine, we have A over H, adjacent over hypotenuse. So we have the hypotenuse on the bottom, which is V. And the adjacent, I said, was Vx. Cool. And for tangent, we have opposite over adjacent, which is adjacent is the Vx on the bottom, division symbol, and then the opposite is the Vy. Cool. And what you place in here inside of the sine function is that question mark symbol, which we are looking for. Remember that this question mark symbol is an angle. It is the same angle as this one over here. If we calculate this angle, we can add it to 180 and we can find the total direction of our triangle. So I have this set up here. And since we are looking for this thing inside of the sine, cosine, and tangent functions, what we have to do is actually basically isolate for the question mark. So here I will write an arrow. And what we're going to do is isolate for this question mark. And how you do that is you take an inverse function on both sides. So if I take just this equation here and I take inverse sign on this side and I put this entire thing in here, and then on this side, whatever I do to one side, I do to the other, inverse sign on this side. Then on this side over here, I have this sign canceling with this sign, and I just isolate the question mark. So that's why I wrote a question mark over here. And on this side, I am left just with this new kind of equation. So that is how you isolate these kind of equations here. And if you guys are okay with that, I'm going to erase this here and bring back my original equation. So I have this here, this whole thing here. So now I can write sine inverse of Vy over V. Here I have cosine inverse. Again, sine, cosine, tangent, and sine inverse, cosine inverse, tangent inverse are all functions in your calculator. You should be able to use those on an exam, or you should be able to look them up online to see what they do. And basically it is canceling one side of the equation to give you an answer for question mark, which is the angle that we're looking for. So here we have Vy, Vx. If we are given the components of the vector, we can calculate the magnitude of the vector, and we can also calculate the angle of the vector using each of the trigonometric identities here. If we are given instead the angle and the magnitude, we can reverse engineer and calculate the components. So let's say the vector is v over here. This is vx. This is vy. And let's say this angle here is theta. So we can set up the same thing. So sine of theta equals opposite over hypotenuse. So, and if you have this guy and this guy, then you can calculate this guy by just multiplying this v onto this side. So you have Vy is equal to sine theta times v. The magnitude and the angle gives you the component. Same thing with the other component. Angle, magnitude of the vector gives you the component. So I just showed you guys how if you have the components, you can calculate the magnitude of the vector using Pythagorean's theorem. And with some trigonometry, you can also find the angle. And vice versa, if you have the angle and the length of the vector, you can calculate the components. Cool. So now that we have all of that done, I'm going to quickly go over some of the algebra. I know I said I was going to save it for a video in the future, but I think it's pretty nice to go over it. So let's say we had a vector which is over here at 2 and 1, and another vector that is at also 2 and 3. So this vector, let's call it A. This vector can be written as x comma y. So we could do 2 comma 3. And this vector B, let's do it in this red color, is going to be 2 comma 1. So you can very nicely do A plus B, which is literally just taking the x components, adding them up together. So that will give us 4, and taking the y components and adding those together. So that'll also give us 4. And this is actually geometrically seen if you take these guys, the vector that goes 2, 1 and 2, 3, if you take one of these and slide it without changing its shape so that you get its tail to the tip of the first one, or you could do that with this one here. You line them up tip to tail like this. you can just measure the length from here, the origin, to the end of this. And this should give you the vector 4, comma 4, this guy here. You can also subtract vectors, so a minus b. This is a little more complicated to do, but how I like thinking about it is, well, you have one vector here and another vector here. If you want to do, like, let's say this is a and this is b, you could just find what negative b is. And what negative b is just b with a negative sign on each of its components. So here we have 2 and here we have 1. Just flip this y component so that it's at the -1 and flip this x component so it's at the -2. This gives you something that is exactly 180 degrees from the original vector. B minus b points in this direction. And I just put a minus sign in front of both of these. I literally take the components of b. B is equal to, what did we say it was, 2 comma 1? And I just multiply this by -1 to get b. I have to distribute this negative sign onto both. And now that you have this, it's just a question of adding, which is the same thing as we've done before. So a, I said, was 2 comma 3. And then I can do plus negative b, which is -2 comma -1. This is negative b. So basically I'm doing a plus negative b. And I can get the answer for subtraction of vectors. So addition and subtraction, I'm sure you guys can work through that and figure out some problems to do with that. We also have the dot product and the cross product. So these guys are kind of unique because the dot product gives you a scalar, a number, and the cross product gives you a vector. So you can find the magnitude of these things. The magnitude of the dot product is AB cosine theta. So if I'm taking a look at A and B over here, I have A, the length of A, B, the length of B, so I can plug those numbers into here, and theta, which is this angle over here. I take cosine of theta, compute all of this, and I get the value of the dot product, which is a scalar. For the cross product, there's a similar identity, except you change sine to cosine. And again, you can get the magnitude by just finding the length of these vectors and the angle between them. This time you compute sine, multiply all these guys together, and you get the length, you get the answer of this, which is the length of this vector. So length of the vector that it equals. And how you find the direction of this vector is you have to do the right-hand rule. So you have vector A, vector B. If I point my thumb in the direction of A and my pointer finger in the direction of B, I get the result, which is perpendicular to both of these, pointing downwards like that. So the length of this guy would be this value, AB sine theta. And how you find the direction of this vector is the right-hand rule. An interesting thing you could try is do the right-hand rule with your thumb in the direction of this guy, pointer finger in the direction of this guy, which is how you have to do it. Thumb with the first vector, pointer finger with the second vector, and your middle finger sticks out and gives you the result of the cross product. But if you do, if you do A cross B, you get this. But if you do B cross A first, your thumb points in the direction of B, and your pointer finger points in the direction of A. So now your right palm is facing up, and the result you get is actually completely vertical, like this, 180 degrees from the original one. So what this tells you is A cross B, oops, sorry about that, is exactly equal to negative B cross A. So when you flip these guys, you spit out a minus sign, which is very important to know. So that is a big overview, big summary of vectors, how you can think of them, components, magnitude, angle, and a very, very quick, brief introduction of algebra. There's also another way to do the cross product. If, for example, we had A is equal to 1, 2, 3. Let's say this was a 3D vector. This is A. And this is B. We have 4, 5, 6. Actually, let's use a bit simpler numbers. We have 0, 0, 3 here. Wait, let's do instead 3, 0, 0. Here we have 0, 4, 0. So if you want to plot these 3D vectors, you have to get a 3D coordinate system like this. The z-axis comes out here. And this first vector, A, is 3 on the x-axis, so 1, 2, 3, and 0 everywhere else. So this is the A vector. Let's do the B vector in red so we can see the difference. 0, 4, 0, and it is 4 on the y-axis, 1, 2, 3, 4, and 0 everywhere else. So exactly these guys here. Now, like I said, if we do A cross B with the right hand, we get the result, which is coming completely out of the page like this in the direction of positive Z. So this is the result, let's call it C. How you can actually compute this, if you have the components, you do A cross B. So if you have the magnitudes, we'll say this whole thing equals C. You can actually calculate the magnitude like this and the direction using your right hand rule. But let's say you didn't have the magnitudes, you had the components. You can also calculate or figure out what C is in terms of components. So here we have, we don't know what the components of C are. From the right hand rule, we can kind of assume that it's going to be some number here and zeros everywhere else. But let's actually compute it. Here's the trick that I have. Which I have learned, but there's other tricks that you can do too. So I have A cross B, and I'm going to do a big thing over here and do X, Y, Z with hats on them. You can also interchange these with I, J, K. It's a way of keeping track. So we have a 3x3 grid, and here I want to fill up the numbers that correspond to the components of these vectors. So the first row here, this one, I will put the components of A, which I said was 3, 0, 0. If you have something more complicated in here, like symbols and not numbers, you can put the symbols in here and it should work the same way. I'm just doing it with numbers here. And the bottom row is reserved for the second vector. Then we complete the box here like this. Then what I'm going to do here is do equal sign. I'm going to do x, open brackets like this, minus y hat, open brackets like this, and plus z hat, open brackets like this. So what I have here is the x component of the result, the x component of this C vector, which I will put here. I have it in front of this little x hat. Then I have a minus sign. This minus sign is very important. It's because the method we're using here is like cofactor determinant thing. So when you have a matrix, you have this like checkerboard pattern of plus signs and minus signs. And for these two, I and K, you have plus sign here and plus sign here. But for the J, for the Y component, you have a minus sign here. So just remember it's written like this, and I'm leaving these open brackets here because of the thing we're going to do right now. So once I have this set up here, I take a look at the X component here. This is what we're going to try to fill up right now. And I just cut off every row and column that includes X. So that is this one and the top one. All right, and that leaves us with a box over here. This box of 4 numbers, I'm going to do a computation with it. The computation is this number times this number minus this number times this number. In this case, we have 0 times 0 minus 0 times 4. So the result of all of that is 0. Now I'm going to move on to the Y. Again, I cover the Y like this, the row and column that includes Y. So you're always going to have this one and then the middle one. Now I have a box of 4 numbers again. Same procedure, same calculation. This number times this number minus this number times this number. 3 times 0 is 0. 0 minus 0 times 0 is also 0. So we get 0 here. Now we're going to move on to the final component. We have the Z, which means we're going to cross out everything, every row and column that has Z, which leaves us with this. And now we have 3 times 4 minus 0 times 0. 3 times 4 is 12. minus 0 is 12. Boom. So what this tells us is that the vector c is actually 0, 0, 12, which is exactly what we were expecting, a vector that is several units on the z-axis, and we figure out here that it is 12 units along the z-axis, and this is in component form. So if you have the components of the two vectors, you can set up this determinant, do this crossing out, calculate these things. You know, sometimes you're not going to have a bunch of zeros here, so these numbers will not be zeros, but this works with any vector. And also, if you want to double check, the magnitude of this guy is 3, right? The magnitude of this vector, the length of this is 3. And the length of this guy is 4. This is 4. So if you want to do this over here, you have A, which is 3, B, which is 4. So 3 times 4 gives you 12. And then sine theta, in this case, the theta between these two vectors is 90 degrees. So if you plug in sine of 90, this gives you 1. So this whole thing here gives you 3 times 4 times 1, which gives you 12. And that is the magnitude of this guy. So two different ways of doing it here. Thank you guys for watching. This is a quick vector and their algebra video. I hope you guys enjoyed, and I'll see you guys soon for part 2 of that lo-fi video. Yep, thank you very much. I didn't go over that number line thing, but anywho, hope you guys enjoyed. See you later.